Thank you. So thanks for giving the chance to give this flash talk. And what I'll talk about is based on the joint work with Ulrich Bauer, Magnus Botnan, and Johan Steen, which has been going on for many years, but we hope that there will be something on the archive within a week or so. So the project is really motivated by questions coming from topological data analysis. So let me maybe explain what that is and what the question is. So very basically, the question is, we got some data and we want to find out some topological information about this data. And when I say topological information, we really shouldn't think something complicated, like maybe we experience topology in university, but really very basic questions, like maybe I can immediately admit that what I'll be looking at is actually H0. So that's really just connected components. So I have some data and I want to figure out how many connected components does this data have. And what do we mean? What do I mean by data? Well, I'm imagining data like just a bunch of points in maybe R2 or RD or whatever. And of course, if I look at points, let's say finitely many points in space closely enough, then there's not a whole lot of interesting topology because every point is actually isolated on its own. And if I look at it coarsely enough, then there's like a big blob of points, and that's not so interesting either. So what I really want to look at is the middle ground between these two. So what I want to do is kind of go from looking at it too closely to looking at it too coarsely, slowly, and see if in the middle somewhere I see something interesting happening. And that's where this starting point here comes in. So what we do is we have our data, and well, the easiest construction I know is just we draw a little ball around each data point, and we take the union of these balls and we call this our topological space given a certain radius. And if I slowly increase the radius in, say, n steps, then I have a sequence of topological spaces that are included in each other. In other words, a representation from an in topological spaces. So what I'll do to that is I'll apply zeros homology, and I'll get a representation of an in vector spaces. And of course, that's something that we like very much because we know the representation theory of an very well. We know the indecomposable, so we can just take the representation we get, decompose it into indecomposables, and then the scheme is set up in such a way that the indecomposables with large supports, that those are really the ones we're interested in, because that means that some feature actually appears for reasonably small radius and keeps existing until the radius gets reasonably large. Okay, what could be the problem with this? So one problem is that there could be problems with our data. So one example of a problem could be that I could have one single data point that's very far away from everything else. I just made a huge measurement error. And if that happens and I just follow the scheme exactly as I said, then what would happen is that, well, basically, no matter what radius I take until it gets huge, I have two separate components, one consisting of all of my data and one consisting of just one single point. And that's obviously not what I want. And also, if I have a somewhat clear picture, but I have like a general haze of data points because there's a lot of randomness in the data, then two different components that should actually be disconnected could be connected by just very few points in between. So what I maybe want to add is, in addition to just taking a ball around each data point, I want to have some kind of measurement of confidence. I'm more confident in some data points because they're close to others than in others or something like that. And that naturally leads me to the situation where I have two parameters. So basically, what I can do is increase the size of the ball, or I can just say I only consider the data points in which I'm more confident. And what happens then is that I get a representation of AM cross AN, where you can imagine the tensor product of the quiver algebras, or just a commutative grid. in topological spaces, and I can take homology again and get a representation in vector spaces. So far, so good. What's the problem here? The problem is that this is almost always wild. So I can, yeah, maybe I can still decompose into, or surely I can still decompose into indecomposables, maybe not as efficiently, but I can still do it. But the indecomposables can look as bad as they want, and what now? So what can we do? Well, we could hope that even though this thing on the right-hand side is wild, we actually only get somehow nice indecomposables when we follow our scheme. So that's really the question I want to ask. So what indecomposables appear as summands of H0, H lower 0, some rep in topological spaces? And if the answer was that only nice ones appear, then that would be very useful to me. Okay, so how can I simplify that? Well, the first step to simplifying it is actually that I can say, since H0 really only measures connected components and connected components are set, it's maybe not so hard to imagine that it's really the same as asking, what about taking representation in sets and then just turning everything into vector spaces? And that turns out that that's equivalent, and that's very nice because then I don't even have to pretend that I'm interested in topology anymore. I'm just going from sets to vector spaces. And maybe as a second step, that's not quite as obvious, but not so hard to see either, is we can even look at pointed sets if we'd like. And then I should admit that we're really not answering this question at all, but we're simplifying it. And instead of looking at this grid, we'll just look at nice quivers. Okay, so let's just look at some of the nicest quivers I know. And well, the nicest quiver, of course, is Dynkin quiver of type A. But there, the answer is not so exciting. Everything comes up as homology of zeroth homology of some representation of topological spaces. Just because the indecomposables of type A are so simple, there's really nothing too interesting happening in the maps anywhere for the indecomposables of type A. So the next thing is type D, and maybe we just look at type D4, and that there's one kind of interesting representation, which is just 3 lines in general position in 2-dimensional space, so something like 1, 0, 0, 1, and 1, 1. And this is not realizable, and the problem is this 1, 1. In sets, we just can't take one element and send it diagonally to 2. But once you think about it, the obvious thing is that you can take 2 elements and both send them to the same thing. So here the answer really heavily depends on the orientation of the quiver. Like, if I take any other orientation of D4, then all representations do come from zeroth homology. But for this particular orientation, we have this representation that does not. And you can extend this to type Dn. Essentially, this result is the same. For type E, we have a result, but that's done by computer help. So we only really know that it's true for the field with 2 or 3 elements. And let me just briefly mention 2 tame types. So for type A tilde, things start to get really crazy in the sense that, well, all pre-projectives, all pre-injectives, and all the things in the non-homogeneous tubes do come from the zeroth homology. And things in the homogeneous tubes only come from zeroth homology if the parameter is a root of unity. Okay, that's fair enough. But if the quasi-length is a power of the characteristic of the field. So it's quite an odd condition that appears there. And then as a final example, let me just mention that for D4 tilde with the orientation that, oh, that's not what I wanted to draw. All arrows go out of a central vertex. Again, everything appears as zeros homology of some representation in topological spaces. So really well, this is still tame, so we don't know any wild examples completely, but our hope that only really nice representations would come as zeros homology is certainly not true. Okay, thanks.
Thanks.